In Chapter 7, we study one section that discusses registers and counters. A register, by definition, is a group of flip-flops that is called a register. So you may have just single one or many. So something like that. We have 4 flip-flops working together. So we call this a 4-bit register. The counter is a special arrangement of a register where the output goes through a predetermined sequence of binary states that is called a counter. For example, if this register produces output such that the first time clock 0000 and then next clock 0001 and then 0010 0011 its binary sequence goes through a predetermined sequence, then that kind of a register is called a counter. Shift register is a register capable of shifting binary information to the neighboring cells. For example, this kind of configuration, for the very first clock, whatever appears on D will appear on output of the first flip-flop. Next clock, the output appeared here will appear on the output of the second flip-flop. While if another value is entering the first one, that will appear output here, and so on. So at every clock, the data in register flip-flop will be shifted to the next flip-flop. So this kind of arrangement is called shift registers. Counters, we have 2 categories of a counter. One is called a ripple counter and the other is called a synchronous counter. The ripple counter is the arrangement of flip-flops are such that output of one flip-flop serves as a source of triggering the other flip-flops. Typically, it's used as a clock to the next flip-flop. That is called a ripple counter. But the synchronous counter, the clocks are all shared from common clock. On each flip-flop, clocks are all shared. So that's a synchronous one. And as I told you, counter is a register, special case of a register. And then if the output tells the binary number sequence, so we call it as a binary counter. So here is an arrangement of a 4-bit binary counter, ripple counter. So this arrangement is using T flip-flop. Remember the behavior of a T flip-flop. The input is 1. If T is 1, the output complements on next clocks. If it was but input T is 0, the output does not change. In this arrangement, input is tied to 1. So for all those flip-flops, input is tied to 1. So all of those flip-flop toggles its output on receiving clock. But the very first flip-flop receives a clock from outside, but second and on, the second flip-flop receives a clock signal from previous flip-flop. So this is arrangement. The output of the flip-flop serves a triggering for another flip-flop that is called a ripple counter. So this is a ripple counter. The output goes through binary number sequence. So this is a binary counter. How does this arrangement goes through binary number sequence? It's as follows. Suppose the input clock we supply this way. So 01, 01, 01 is a keep repeating. Then this T flip-flop is a falling edge triggered. So if a clock goes down, output toggles. Since T is tied to 1, output always changes to its complement. So we say it's toggled. So, but on falling edge of the clock, the output changes. So as to output of the first flip-flop, that toggles when clock goes down. So when clock goes down, output toggles. When clock goes down, output toggles up. When clock goes down, output toggles up. When clock goes down, the output changes up, and so on. So the A0, the output of the first T flip-flop, has this kind of a bit pattern. And that is fed to the clock of the next flip-flop. So the A1, output of the second flip-flop, A1 changes, toggles when A0 goes down from 1 to 0, falling edge. So the falling edge of the A0, A1 toggles. Falling edge of A0, A1 toggles. Falling edge of A0, A1 toggles. Falling edge of A0, A1 toggles. So this is the output pattern on A1. Similarly, A2, clock comes from A1, so the falling edge of the A1, A2 toggles. Falling edge of A1, A2 toggles. Falling edge of A1, A2 toggles, and so on. So this is a pattern for A2. Similarly, A3 receives a clock from A2, so falling edge of A2, A3 toggles. Falling edge of A2, A3 toggles. So this is the bit pattern, output pattern for all those 4 flip-flops. So as we read the data at the very beginning, those 4 output is 0, 0, 0, 0. We didn't have any clock counting yet. We didn't have any 1 yet. But by the time we have a 1, by the time we have a falling edge, the output becomes a 0, 0, 0, 1. So when we have a first 1, those 4 bits become 0, 0, 0, 1. And as we have another 1 from the input, as it goes down, the output pattern on these 4 flip-flops are 0, 0, 1, 0. So 0, 0, 1, 0 means a binary number, decimal 2. So we had 2 ones. By the time we have 3 ones, the output becomes 0, 0, 1, 0, which is 1, 1. I'm sorry, this is 1. So we have 3. By the time we have 4 ones, output is 0, 1, 0, 0, which is 4. So the pattern, output pattern of the flip-flop represents how many ones we have received on a clock input. So we say we can count how many ones are coming in by these 4 flip-flops we have arrangement. So this is called a binary ripple counter, and the 4-bit. We can do similarly with the D flip-flop, and D flip-flop, by having complement output connected to D, so on next clock, the output toggles. So we achieve a T flip-flop by having this one. Also, we can configure with a JK flip-flop. Then it's quite simple. And in JK flip-flop, if both J and K's are 1, then output toggles like a T flip-flop. So what you do is just tie JK input together and consider that as T flip-flop. So you can implement a ripple binary counter using JK flip-flop as well. So here's his table, how the output is produced from those 4 flip-flops. So we achieve a binary counter sequence. And synchronous counter, which is by definition flip-flops receive clocks from common source, not one flip-flop derives the other one. In that case, to achieve the binary sequence, we should control when the flip-flop should toggle. So using those logic, you can implement the synchronous counter. And the ring counter is a circular shifter register. is a ring counter, and we have 4 registers. They are connected as a serial shift registers, but the very last one is connected to the input of the first one. So if we begin with 1 0 0 0, only one single one in all those flip-flops done. On the one clock, one shifts to the next, and then another clock shifts, and then goes back. So we have a circular shift that is called a ring counter. Using this kind of arrangement, you can generate the signal in a sequence. So for example, if we have a 2-bit counter, so we have a 0 0 0 1 1 0 1 1, and it goes back to 0 0, and then if this counter runs forever, if those output of the counter is fed to the 2x4 decoder, then when input is 0 0, only this signal is 1, 0 1, and next one, and the 1 0, next one 1 1, and next one, and it comes back to 0 0 and 0 again. So we have this kind of a timing diagram. So typically in a computer system in CPU, so the CPU works for one job, one instruction. It needs to have a 4 sequence of work needs to be done. For example, it first reads the instruction, and then fetches the operands, and then operation is applied, whatever it is, add operation or add operation, and then the result is stored back. So those 4 stages should be done in time sequence. Then how do we control that? Using this kind of arrangement, and then this part we enable the very first stage. Get the instruction, fetch the operands, and then do the operation, and store the result back, and then it repeats. It repeats those 4 stages. So this is how to generate a sequence of timing signals. Johnson counter is a variation of a ring counter where you can represent double the states a typical ring counter can represent. Remember in previous slide, if you have 4 flip-flops in a shift register configuration, and then a circular connection, then since only one of those is 1, as you go through the sequence, you can have only 4 different patterns you get. So you can have only 4 states with 4 flip-flops. But Johnson counter is another arrangement such that with 4 flip-flops you can represent 8 different states. So with the K flip-flops you can represent 2 times K states. That's a Johnson counter, and the configuration is something like this. So you have 4 D flip-flops. It's configured as a shift register, but what you can see here is that on the very last one, the complemented output is connected to the input of the very first flip-flop. And what happens is that if you begin with all zeros, output all zeros, then since complement is 1, on next clock, the first one becomes 1. So beginning with all zeros, on next clock, because of this red connection, first one becomes 1, and then 1 is shifted to the next, to the next, and to the next. And then since output is 1 here, the complemented output is 0, so 0 is fed back to the first flip-flop. On next clock, 0 is shifted, and 0 is shifted. On next clock, you will fill with all zeros. You go back to first pattern. So as you can see, with the 4 flip-flops, you can distinguish 8 different states. So that is a Johnson counter configuration. But to distinguish 8 different patterns, you don't have to decode all those 4 outputs. Instead, you can just decode 2 of 4. So for the first pattern, A and last one, first one and last one is both are zeros, so no other pattern is such. So to detect the first pattern, only those two outputs needs to be configured, detected or decoded. And the second pattern, the first one and second one is a 1, 0. It never appears in any other state. So those two are sufficient to detect the second pattern. And third pattern is the second and third one. Second one true form, third one is complemental. So this 1, 0 never appears in any other, and the like. So this is what you need to decode to detect the pattern. So with this configuration and decoding only those 2 of 4 outputs, you can distinguish 8 different states. So this is called the Johnson counter.